Hi guys, welcome back to the channel. In this video we are going to discuss MOD-6 counter. So let's get started. So in the previous videos we already discussed about full modulus counters. So those are MOD-4, MOD-8, MOD-16, that kind of counters. So we also discussed MOD-5, MOD-10 counters, but in this video we are going to discuss MOD-6 counter. So if you consider the first step is to find the number of flip-flops. So we can identify, as we are going to have total 6 states or 6 transitions. So we are going to have the 3 flip-flops. How? 6 means what? So 6 means in binary, that is 110. So basically we are having 3 bit of information. So 3 bit means 3 flip-flops we are going to use for that. So these are the total 6 states that we are going to see. So starting from 0 ending at 5. So 0 1 2 3 4 5 again going to 0, and like that this sequence continues. So using K-map, this is the first method. This is nothing but how many terms we want. So what is the mod count? So here the mod count is 6. So up to the mod count we are going to have a reset logic Y. So with the help of this logic expression Y, we are going to have some logic building circuit. With the help of the circuit, we can reset our whole things or whole flip-flops to 0. So if you observe the reset logic Y, so up to 5 we are going to have ones. All the things would be 1. So 6 and 7 we don't want, because at 6 only we are going to apply some logic. So at 7th position also we don't want. So for that we are going to have all the min terms in the K-map, that is, as these we have 3 variables, that is Q0, Q1, Q2. So Q0 is row wise, Q1, Q2 I took column wise. So total starting from 0 to 5 I took all the min terms in that. So we are now going to group them. So in this video, MOD-6 counter only we are going to implement by using 2 methods. So basically we had 2 methods to implement all these kind of mod counters. So the first one is using K-map. Second one is a simple logic with the NAND gates. So in the previous MOD-10 counter we had discussed 2 things. So if you missed that video, I am giving that video in the description box. Please check it out. So first using with K-map, let's see start. First of all, we need to understand a point here. So starting from 0 we are going to up to total 5. So these are total 6 terms or 6 transitions. So after passing the 6 transitions, that is MOD-6 counter, after counting 6 transitions, if you saw the next transition is 6, that is 110. So if you see that 110, you are going to apply some logic on that 6, and we are going to go back. So we don't want that 6 and we don't want that 7. That is so that we are the reason that we are going to apply some logic on 6, and again we are going to have the clear inputs. Clear means what? 0 0 0. Again it will, all outputs will be cleared from to 0. So with the help of clear inputs we can achieve that situations. So whatever may be the outputs Q0, Q1, Q2, so in that situation, in the 6th position again we are going to trace back to 0, and we are going to obtain this MOD-6 counter. So you can see we can make a group of 2 4 elements, that is 0 1 3 2, and second one is 0 1 4 5. So these two groups are represented as Q0 bar plus Q1 bar. So this is our final output expression, Y is equals to Q0 bar Q1 bar plus Q1 bar. So we are going to have this reset logic in the combinational circuit for the 3-bit counter. First of all, we need to understand an important point. If you want to build any of the logic circuit or the counter that we want the lower thing, so then the 2 power n. So first of all, we need to consider the 2 power n counter, so that we can we can have combination circuit and we can achieve our required mod counter. So for that purpose, I am going to take mod 8 up counter. So why I took mod 8 counter only? I cannot mod 16 counter, because mod 6 is very close to the mod 8 counter. So that is the reason I took 3 counter, 3-bit counter I took. So next thing, we are going to apply the clear to the all flip-flops. So if you see the clear, that is active low inputs, because the bubble is also there for the each and every flip-flop. Now the output expression can be evaluated as Q0 bar plus Q1 bar. So if you have seen that in between we have plus operator, means an OR gate. So if you cleanly see the truth table, means the circuits, we have already had the outputs Q0 bar and Q1 bar. So simply take that to the OR gate and simply merge that Y output Y to the clear. So this is the simple circuit that I am showing here. So this is the MOD-6 counter. We are now going to see the second representation also. Now we are going to start the second representation, that is a simple logic with the NAND gate. So if you observe the NAND gate, all the inputs are 1, then the output would be 0. This is the main logic of the NAND gate. So this we have to remember. And the second important point is we are going to apply some logic on the 6, and we are going to have the circuit. So the 6 expression in binary is 110. So remember that is very important, 110, and we are going to have all the inputs for the NAND gate as 1, so that we are going to obtain output as 0. In the second method also we are going to have the same thing. First of all, take the upper counter, the main counter, the big counter, that is mod 8 up counter here. So if you observe the truth table, we are going to stop at the 6th position and we are again going to 0. So in this case also we are going to reset our all flip flops when 1 1 0, that is Q0 Q1 Q2 as 1 1 1 means 1 1 0. We are going to reverse them as 0 0 0 with the help of NAND gate by passing clear as 0. So there might be many bunch of couple of representation of a single circuit. Now we are going to see some of them. So some of them we are going to see now. First one that is, so 6 is 110, that is ABC. So ABC means what? The each and every flip flop has output. So the first flip flop output is A, the second flip flop output is B, like that. The third flip flop output is C. So if you observe 6 means what? 110. So when the first flip flop A is equals to 1, it will be directly input as to the NAND gate. So the second flip flop B is 1, so take directly to the NAND gate. But the third flip flop output is 0 because 6 is 110, right? So the third flip flop we are not going to take directly 0. We are going to apply a NOT gate and we are going to take it as 1 because all the inputs for the NAND gate should be 1. So if you pass all the 3 inputs to the NAND gate as 1, then the output would be NAND gate for the is 0. So 0 is directly applied to the clear, then all the flip flops would be resetted to 0 when this state occurs, that is 110. So before the state terminates only, we are going to obtain the new state, that is 0 0 again. Means after 5 we are again going to get 0, we are not going to get 6. Now we are going to observe a clean observation here. So instead of having the C, already we are having the C bar. Instead of using the NOT gate, we can also simply use the 1. So simply we are going to pass all the 3 inputs as to the NAND gate as 1 1 1. So instead of using the C, we can simply use the C bar for the third input of the NAND gate. So in this situation you can also observe I did not change the output, that is again 1 1 0. So in this situation also the whole output would be 0 again because the NAND gate output is 0. We are applying in that situation clear as 0. So in the internets or some places also you might see these kind of representations also. So I said before earlier, there are bunch of couple of ways to represent a single circuit. So you can represent in this format also, like you can represent the inputs here also. So taking simply NAND gate in the down row itself and passing A, B and a C. So truly speaking, that is C bar. For if you see that ABC as that is 110, again we are passing. So the input for the NAND gate is again 111, the output is 0. So 0 is directly applied to the all flip flops. It will be after that state, the whole output would be again 0. So that becomes the mod 6 counter. This is the state diagram for the mod 6 counter. So the orange highlighted one is the up counter and the blue highlighted one is the down counter. So as we have total 6 states, we are going to start from 0 and end at 5. If you want the mod 6 counter down counter, start with 5 and end at 0. So this is the sequence or state diagram for the mod 6 counter. I hope you understood this video. Thanks for watching up to now.